Hi and welcome back. So over the last bunch of videos, we've been dealing with electron configurations and talking about, I guess, maybe it hopefully gave you a little bit more of an idea of what an atom would look like up close if we were able to see one. And one of the things I kind of realized I haven't done too much over the past bunch of videos where we've been doing electron configurations. We've been writing out a lot of, a lot of electron configurations where we say, okay, we've got these s orbitals, and then we've got, these p orbitals, and I've never really drawn or given you an example of what those might look like. So in the first part of this video, I kind of want to maybe draw a little bit that would more or less hopefully give you a bit of an intuition as to what an atom would look like up close. And if you're really wondering about that, the Khan Academy has got some great videos on giving you an intuition as to what the orbitals would actually look like when they're stacked on top of each other. But what I want to do in this video is maybe I'll draw a little bit of that, and I'll actually draw that right now. So if we were to take a look, let's actually say we were going to take a look, let's say at neon. Neon should be okay to draw. So remember, we've got our nucleus in the center, and what is neon's electron configuration? I'll write it down here. So neon. Neon's electron configuration, well, we're going to have our 1s orbital, 1s, and it's going to be completely full, so 1s2. Then we'll have 2s2, so these two electrons, lithium and beryllium, are full, and that's kind of how I keep track of it. I sort of count across the periodic table, just filling up orbitals until I get to the element that I'm filling up the orbitals for. So we filled up our 2s orbitals. And then after that, we're going to fill up our 2p orbitals. And those are going to be all the way full, right? We're going to have 2p6. Hopefully this is review. I think I've even done neon's electron configuration in a previous video. So hopefully you understand that. If you don't, you can go back and watch the videos on electron configurations. But anyway, this is neon's electron configuration. And one of the things that I had been doing in the past few videos was I showed you the probability function of our 1s orbital, which was really just a sphere, right? So if we said our nucleus was that purple dot in the center, then this blue circle that I've just drawn, this is going to be our 1s orbital. And remember, we have a greater probability of finding electrons towards the center of this 1s orbital than we do towards the edges of the 1s orbital. But it's essentially just a sphere. It's a sphere of probability of finding an electron. It's a spherical orbital. Then on top of that, we have our 2s orbital. And what does the 2s orbital look like? Or what do you think it should look like? Well, it's just going to be a shell, essentially. It's going to be like, if you imagine like a hard-boiled egg. Imagine you add, this purple part is going to be all of our, you could say the egg white, and then this blue part in the center could be the egg yolk. That's what essentially our 2s orbital would look like. And let me label this now. So we have, this is going to be our 2s. So it's just going to really be, again, if you looked at it from the outside, it's a spherical looking orbital, but it really is going to be more of a shell because, it has this hollow point in the center that's occupied by the nucleus and by the 1s orbital. So, and again, we've got greater probability of finding an electron further towards the nucleus. So there's greater probability right around here. This is the greatest probability of finding an electron is sort of right on the edge of our 1s orbital. And then as we move out, we have less and less probability of finding an electron. Now, what do these p orbitals look like? So we've got a good idea of what our 1s and 2s orbitals look like. What do the p orbitals look like? And I'm sorry, I forgot to, I don't have my, graphic of all the different orbitals up, but the p orbitals are easy enough to draw, because if we just took a three-dimensional plot system, so we said that, there we go, so we said that this is going to be our x-axis, this is going to be our y-axis, and this is going to be our z-axis. We've got three different p orbitals, right? So 3 different p orbitals times 2 electrons per orbital lets us put 6 electrons into our p orbitals, right? So now, what essentially happens is we get these dumbbell shapes around our nucleus along each of these axes. So we could say along the x-axis, we get a distribution like this. That's essentially, it's more or less a dumbbell shape. It's got like a fine point in there that points in towards the nucleus. And then along the other end, along the other edge of our x-axis, we've got a similar orbital. So we've got kind of, you could imagine that the orbitals look like that. And so if I was going to draw that here on this orbital, it would essentially look something like this. Actually, you know what? I'm going to choose a different color so we can differentiate between these orbitals. So we could say that this is going to look something like our 2p orbital, or at least one of our 2p orbitals. So, and it's going to have 2 lobes sticking off of either end. So this is going to be 2p, and we'll call that 2px. 2px. And we know that we've got three p orbitals, right? Because we can fit 6 electrons into those orbitals, 2 electrons per orbital. So we know that we've got to draw 2 more of these. So let me just go ahead and draw those. So we could say that maybe this would be our py orbital. And I'll just say that, we've got some probability out here of finding an electron. And you could imagine, and hopefully you're understanding this right now, but if you're not, don't worry too much about it, because we will talk about this much more in the future. But hopefully you can see, if we go back to our coordinate plane, and let me actually just draw this again. So if I say that I've got x, z's up there, and y's over here, for my py orbitals, are just going to be going along this axis. It's going to go along the y-axis of our coordinate system, you could imagine. So you could also imagine, well, what is the angle going to be between this lobe of our px and this lobe of our py? Well, that angle should be 90 degrees, right? So hopefully, I might be confusing you with this, but hopefully it's not that confusing. And if it is, I'd say don't worry, because this will definitely come back in the future of the playlist. So anyway, you could say that these in yellow are px, these in purple are py, and then we've got one more to draw, and we could say that these 2 lobes right there, these are going to be our 2pz orbitals. So if we were able to more or less look at an atom, or get a graphic representation as to, maybe what an atom might look like, what an atom might, where the electrons and where the orbitals might be on an atom, this is an okay representation as to what it might look like. We've got this spherical shape, and then sort of meshed in with the spherical shape, we've got these lobes that occupy, I guess, the x-coordinate. If we place the origin of this coordinate system at our nucleus, we've got our x-axis, we've got our y-axis, and we've also got our z-axis. Now, one thing I just want to talk about a little bit, and this kind of introduces the next topic, and the next topic that we're going to be talking about in the playlist. Let's imagine, so we said that this was a neon atom. And let's just say instead because I've been telling you for a while that atoms are non-reactive, and I haven't necessarily said why, and I'm getting to why in the playlist, but let's just say that instead of drawing out a configuration for neon, let's say we were instead drawing out a configuration for fluorine. So fluorine is right there on the periodic table, and we know, and let me actually I'm going to erase neon. What's the big difference if we were going to change so I'll say if we were going to say that this was fluorine, what's the big difference if we were going to change, or really the only difference, if we were going to change this electron configuration to be that of fluorine and not that of neon? Well, it's just the number of electrons in our 2p orbital, right? We've got 6 right now. So if I crossed off 6 and said 2p5, that would give us the electron configuration for fluorine, right? And it would still look reasonably, if we were going to draw some type of depiction as to what the atom would look like, it would still look reasonably similar. So now let me ask you this question. And I'm going to scroll up here. And actually, you know what? I am going to try. Actually, yeah, this might work out really well. There we go. I am going to try edit, copy, edit, paste. Oh yeah, that actually did work out pretty well. So now imagine that I had, and I'm just going to erase some of this extra stuff. There we go. Just erase some of these labels, which I probably shouldn't have included in the first place, but I can erase them. Okay, there we go. So now imagine I have this fluorine atom. So imagine now we've got 2 fluorine atoms. And how can let's see if I can, no, that's not what I want to do. So layer 2, no. How about, I'm trying to move this, oh, there we go. Okay, so now imagine I've got these 2 fluorine atoms. I've got these 2 fluorine atoms together, and imagine I'm going to try to react both of these fluorine atoms. And we know, I think I've told you in the past, that what is going to react, and hopefully you can see from this depiction, what is going to react is going to be the electrons on our fluorine atoms. That we've got our protons and our neutrons, they're all tucked away into the nucleus that only occupy 1/10,000th the space of this entire atom. And now imagine I was going to react these 2 atoms of fluorine, and I were to push them together and overlap them on top of each other. Which electrons in this atom are going to react? Is it going to be these electrons in blue that are in our 1s orbital? Are they going to react first? Or is it going to be these second level electrons, these 2px electron, or these 2p orbital electrons, and also the 2s orbital electrons? Well, it's going to be the 2s orbital electrons, right? They're further out from the nucleus, so you can imagine that, here I'll start drawing again. You can imagine that our nucleus, so the nucleus in here, has got a positive charge, and everything around the nucleus, so everything else around the nucleus is negative. And as these electrons get further and further out, so as they grow further and further out from the nucleus, they are going to essentially, they're going to see less of the charge of the nucleus, and therefore it's going to be easier for them to, I guess, react with other atoms that might be around them. So therefore, it's going to be probably when these two, well, what happens when these two atoms react with each other is it's going to be these outside electrons. It's going to be these electrons in our, let me switch colors again. So it's going to be the electrons that are in our 2s orbital, and I should have a 2 there. It's going to be our, also all of these 2p orbitals. And this is exactly where the concept of valence electrons. Valence electrons. This is exactly where, I guess, the concept of valence electrons comes from. And essentially what you can, the intuition that I want you to get behind what valence electrons are is they're the outermost electrons, or the electrons that are going to react. They're the electrons that are the most likely electrons to react for a given atom. So anyway, that's enough for this video. In the next video, I'll give you some more specific information on valence electrons and how to count valence electrons and what counting valence electrons actually does mean about the reactivity for a bunch of different elements. So anyway, thanks for watching, and I'll see you in the next video.